I want you to picture yourself standing outside on a truly perfectly dark night.
Oh, yeah. The kind of dark where your eyes take like 20 minutes just to adjust.
Exactly. You know, you're far away from city lights, far from the street lamps, the headlights. Maybe you're out in the desert or, I don't know, deep in the mountains.
Just zero light pollution.
Right. And your eyes have finally adjusted to the absolute pitch dark. And as you look up, you see it.
It's unmistakable when you really see it.
It is. It's this faint, glowing, milky band of light stretching entirely across the sky.
Yeah.
And, you know, for most of human history, anyone who looked up saw that exact same glowing river.
But nobody had the faintest clue what it actually was.
Which is wild to think about. Today, we are taking a deep dive into an excerpted essay that explores the deep science and, well, the history of the night sky. Specifically focusing on our own cosmic neighborhood.
It's a really fascinating piece of writing.
It really is. Our mission today is to understand exactly what you are looking at when you gaze up at that glowing band, how it got there, and what its violent past tells us about our future.
Because every ancient culture had a story to explain that band of light, right? I mean, the ancient Greeks looked up and imagined it as a literal river of spilled milk.
Which is actually where we get the word galaxy.
Right, yeah.
It traces all the way back to the Greek word for milk.
Yeah.
But the modern scientific reality detailed in this essay is, well, it's infinitely more poetic and deeply humbling.
Oh, absolutely.
That faint band of light isn't just some, like, celestial decoration painted on the roof of the sky. It is our home.
Yeah, you are looking at the combined glow of hundreds of billions of distant suns that make up our own galaxy, the Milky Way.
But you're seeing it from a very specific, almost deceiving vantage point, right?
You are looking at it edge-on from the inside. We are, riding along on one single star, looking out through the dense, flat disk of our own galactic home.
So the view is a river of distant suns, because we are just floating right in the thickest part of it.
Exactly. We're embedded in it.
Okay, let's unpack this. Because to really wrap our minds around what's happening inside that glowing river, we need to establish the sheer scale of a galaxy.
Right, because galaxy is a word we throw around a lot in sci-fi and pop culture.
But holding the actual physical concept in your head requires some major mental gymnastics.
It really does. For anyone without a science background, a galaxy at its most basic level is a massive, sprawling collection of stars, enormous clouds of gas, and cosmic dust.
Just a giant collection of stuff.
Yeah, and all of this material is bound together by the force of gravity, and it all orbits a common center. In the case of the Milky Way, we are talking about a structure containing somewhere between 100 and 400 billion individual stars.
Which is just a staggering number. I mean, let's ground those massive numbers in something tangible for you listening. Imagine a giant, flat breakfast pancake.
Okay, a pancake.
Yeah. Now, take a single chocolate chip and bury it halfway between the center of that pancake and the outer rim.
I like where this is going.
That one chocolate chip is our entire solar system, everything we know. When you look up at the night sky and see that milky band, you are standing on that chocolate chip, looking out sideways through the batter towards the rim of the pancake.
And you're seeing the combined glow of all the other chocolate chips stacked up along that flat plane.
Right. You're seeing the cross-section of the pancake.
The geometry of our situation maps perfectly to that visual. And the essay expands on this scale by looking at the space outside the pancake, too.
Like the rest of the breakfast table.
Kind of, yeah. In the universe at large, galaxies are the fundamental building blocks. You can think of them as bustling, isolated cities scattered across a vast, profoundly empty continent.
So the space between them is it's just nothing.
The gulfs of nothingness between these galactic cities are so incredibly wide that the galaxies themselves become the basic units of cosmic structure.
And within our own bustling city, our sun is completely unremarkable.
Very average.
It's a very average star just sitting out in the galactic suburbs. But the timeline of our orbit around the center is what really grounds you, I think. Just as the Earth orbits the sun, our entire solar system is orbiting the center of the galaxy.
Yeah, the entire structure is in motion. It's not static. And it takes our sun roughly 230 million years to complete a single lap around the galactic center.
Wait, 230 million years? Just for one lap?
One single lap.
That means the last time our planet was in this exact physical spot in space, dinosaurs hadn't even appeared on Earth yet.
Not even the earliest dinosaur.
That is insane. Our planet has been through entire epochs, mass extinctions, the complete evolution of humanity, all while barely moving a fraction of an inch along our cosmic racetrack.
It really forces a shift in how we perceive time, doesn't it?
It really does.
And if we pull back from our solar system and view this entire rotating structure from the outside, the shape of it tells us a lot about its history and its behavior.
Right, because not all galaxies look like pancakes.
No, not at all. Galaxies generally fall into a few broad categories. You have ellipticals, which are round, smooth, almost featureless blobs.
Blobs in space.
Basically. They are dominated by older stars and have exhausted most of their gas, meaning very few new stars are being born there. They are the quiet, retired communities of the cosmos.
I love that. Retired communities.
And then there are irregular galaxies, which lack any symmetrical shape at all. They are often messy and chaotic, usually because their gravity has been disrupted by a close encounter with a neighboring galaxy.
But the Milky Way falls into the most photogenic category, right? We are a spiral galaxy.
We are indeed.
We have that flat rotating disk with a bright central bulge of stars and these beautiful, graceful arms winding outward like a massive pinwheel.
It's the classic image everyone thinks of.
Right, but I have a question about that. When we see pictures of spiral arms, it looks like a solid wheel spinning. Are those arms actual solid physical structures? Like spokes on a bike?
So glad you asked that. Thinking of those spiral arms as solid structures creates a huge physical paradox.
How so?
Well, if they were solid physical objects, the outer edges of the arms would have to travel at impossibly fast speeds to keep up with the inner edges.
Oh, because they have a much longer distance to cover in the same amount of time.
Exactly. So if they aren't physical spokes, what creates that distinct, sweeping pinwheel shape? What's fascinating here is the essay uses a brilliant, everyday analogy to explain this visual illusion.
I'm ready for it.
Those spiral arms are actually cosmic traffic jams.
Traffic jams?
Yeah. Imagine driving on a highway where a slow-moving truck is in the right lane. Cars naturally bunch up behind the truck, creating a dense, slow-moving cluster of traffic.
Okay, I know that feeling well.
We all do. Eventually, individual cars manage to pass the truck and speed back up, spreading out again. The traffic jam itself, the dense region of cars, stays roughly in the same place on the highway, even though individual cars are constantly flowing into it and then back out of it.
Oh, wow. So the spiral arms are regions of higher gravitational density.
Precisely. As clouds of gas and individual stars orbit the center of the galaxy, they hit these dense regions and slow down. They pile up.
And when giant clouds of space gas get compressed together in a cosmic traffic jam, the gravity causes them to collapse inward. And I assume the pressure and heat becomes so intense that nuclear fusion ignites.
You got it. The compression triggers a massive wave of starbirth. The arms of a spiral galaxy are brightly lit, not because they are solid structures, but because they are active stellar nurseries.
That makes so much sense. And the essay mentions this process completely dictates the colors we observe in different parts of the galaxy.
It does, because the spiral arms are full of brand new, incredibly hot, massive stars. They glow with a brilliant blue-white color.
While the central bulge of the galaxy glows in shades of yellow and red.
Right, because the center is packed tightly with much older, cooler stars that have been burning for billions of years.
So you essentially have a color-coded map of the galaxy's demographics just by looking at the light. Blue and white in the spiral arms where the new stars are actively igniting, and yellow and red in the center where the older population resides.
Yeah, you can read the age of a galactic neighborhood purely through its color temperature.
Here's where it gets really interesting, though. If this entire massive structure is spinning at millions of miles an hour, there has to be an anchor.
Right. Gravity requires mass.
Exactly. For hundreds of billions of stars to orbit a central point without just flying off into the void of space, whatever sits at the absolute core of that yellow-red central bulge must be incredibly dense. What is actually in the middle?
At the very center of the Milky Way, and at the core of most large galaxies, is a supermassive black hole.
A supermassive black hole.
Yes. Ours is named Sagittarius A star. And to grasp the density we are talking about, this single object weighs roughly 4 million times as much as our sun.
4 million suns.
But all of that mass is compressed into a physical region no larger than our own solar system.
See, but this is the thing. A black hole is, by definition, an object with gravity so intense that not even light can achieve the escape velocity required to break free from it.
Right, they are totally black.
Which means it is completely invisible. And the center of the galaxy is packed with billions of stars and massive, thick clouds of dust. Looking toward the center should be like trying to see a single unlit street lamp through a dense fog.
It's a logistical nightmare for astronomers.
So how did astronomers actually prove it was there, let alone calculate its exact weight?
Well, the scientific process behind this actually earned a Nobel Prize. Astronomers knew they couldn't look for the black hole itself, and visible light is indeed blocked by all that galactic dust you mentioned.
So what do?
They used telescopes equipped to see infrared light. Infrared light has longer wavelengths, which allows it to slip right through the dust grains and travel all the way to Earth.
Oh, that's clever.
By looking at the infrared light, they focused on the individual stars closest to the very center of the galaxy, and they simply watched them, mapping their exact positions year after year after year.
Just tracking their movement.
Exactly.
Because if you track a star over a decade and watch it whip around a completely empty-looking patch of space at a fraction of the speed of light, the math reveals the invisible object.
The laws of gravity are strict.
Right. To force a massive star to turn that sharply and move that fast in a tiny, tight circle, the invisible thing it is orbiting has to possess an immense, specific amount of mass.
Yeah, by measuring the speed of those stars and the exact size of their orbits, astronomers could calculate the exact gravitational pull required to keep them on those paths. The mathematics proved that an object weighing 4 million suns had to be hiding in that tiny, dark space.
That invisible, immensely heavy anchor is Sagittarius A star.
It is.
It is an eerie realization, you know. You look up at this beautiful, stately river of milk in the sky, and the whole thing is organized around a literal gravitational monster lurking in the dark.
It is a bit spooky, but the essay makes a point to reassure us. Sagittarius A star is located tens of thousands of light years away from our solar system.
So we're safe.
Very safe. And for a supermassive black hole, it is actually quite docile. It isn't actively consuming huge amounts of material right now, which means it isn't violently tearing stars apart or blasting out dangerous radiation. It is simply sitting there, quietly providing the gravitational anchor for the inner galaxy.
Which brings us to the origins of this massive structure. We know what the Milky Way looks like today, and we know what anchors it. But going from a completely empty, expanding universe to a spinning pinwheel of 400 billion stars, that requires a building process.
It does. We have to look back to the early universe, shortly after the Big Bang.
Okay, setting the time machine.
The cosmos was a vast, expanding fog, mostly made of hydrogen and helium gas. It was largely uniform, but there were microscopic variations, places where the gas was just slightly denser, slightly clumpier than others.
And where there is a clump of matter, there is a slightly stronger gravitational pull.
Exactly.
That slightly stronger gravity pulls in more neighboring gas, making the clump bigger, which makes its gravity even stronger, creating a snowball effect.
That is the basic mechanism of how structure forms. However, there's a catch.
There usually is.
When astrophysicists run the mathematical models using only the ordinary matter, the hydrogen and helium, we can actually observe the timeline doesn't work. There simply wasn't enough gravity from the ordinary gas to pull a massive galaxy together as quickly as the Milky Way formed.
Oh, I see.
The spinning gas would have flown apart. There had to be a massive amount of unseen mass holding it all together. This invisible ingredient is dark matter.
Right. Dark matter is the stuff we can't see, can't touch, and doesn't interact with light at all. But its gravitational pull vastly outweighs all the ordinary matter in the universe combined.
Exactly.
So is it basically like the invisible steel rebar hidden inside a concrete building, giving the visible universe the structural integrity it needs to exist?
That's a great way to think of it. If we connect this to the bigger picture, the essay uses a concept of cosmic valleys to explain how dark matter guided the creation of galaxies.
Cosmic valleys.
Yeah. In the early universe, this invisible dark matter clumped together and formed a massive, interconnected scaffolding across space. It created dense gravitational regions.
Okay, so if the dark matter forms the underlying landscape, creating deep gravitational valleys, then the ordinary hydrogen and helium gas acts like rainwater.
That's spot on. The ordinary gas naturally flowed toward the strongest sources of gravity. It fell into these unseen dark matter clumps, pooling in the deep gravitational valleys.
Like puddles forming after a storm.
Exactly. It was deep within these invisible dark matter wells that the hydrogen gas got dense enough and hot enough to finally ignite. That specific process is what birthed the very first stars, and those dense pools of gas and stars became the first small galaxies.
So everything we can see, every glowing star, every nebula, every spiral arm, is entirely shaped by a framework we cannot see. The visible universe is just the glowing dust resting in the valleys of invisible dark matter mountains.
Beautifully said.
But wait, those early dark matter pools only created small, early galaxies, right? The Milky Way is a behemoth.
Right, so how did it get so big? Galaxies do not remain static. The crucial mechanism for how giant galaxies like the Milky Way attain their staggering size is through merging.
Merging, like corporate mergers.
A little more violent than that. Over billions of years, driven by the relentless pull of gravity, smaller galaxies drift toward one another. They collide, their gravitational fields tangle, and they fold into each other. Large galaxies are built by consuming smaller ones.
Which is wild. And we actually have physical proof of this violence written into the sky.
We do.
The European Space Agency launched a spacecraft called Gaia. Its entire mission was to map the precise positions, velocities, and chemical compositions of over 1 billion individual stars within the Milky Way.
It's an incredible undertaking.
Right. By measuring a star's chemical signature, like a unique barcode of light, it emits based on what elements it is made of. Astronomers can tell where that star was born.
And the Gaia data revealed something amazing. It found streams of stars moving through our galaxy in highly unusual coordinated groups.
Just moving together like a school of fish.
Exactly. These specific star streams share the exact same chemical signatures, which are different from the native stars of the Milky Way, and they share the same orbital trajectories.
Wow.
The data acts as a fossil record, proving beyond a doubt that these stars are the shredded remains of smaller galaxies that the Milky Way swallowed whole long ago.
So what does this all mean? Is our beautiful galaxy actually a Frankenstein monster built out of shredded neighbors?
I mean, yes. The Milky Way is literally built from the bodies of its neighbors and is still cannibalizing small companion galaxies today, pulling them apart with its gravity and adding their stars to our outer halo.
We are living in a predator galaxy.
We really are. But this raises an important question about our own future. We are not the only massive galaxy in our local cosmic neighborhood.
Oh boy.
The Milky Way has a near twin, the Andromeda Galaxy, located roughly 2.5 million light-years away. And the two of us are caught in each other's gravitational pull, actively falling towards one another through space.
Okay, so in roughly 4 to 5 billion years, the Milky Way and Andromeda are going to collide. We will merge into one single, unimaginably massive supergalaxy.
That's the current forecast, yes.
And I'm sure you listening might be panicking right now, picturing our sun crashing head-on into another star, or planets colliding like billiard balls in some apocalyptic demolition derby.
It sounds like a violent, destructive event. But this is where the sheer mind-bending scale of empty space comes into play again.
Right, because of how far apart things are.
Exactly. The distances between individual stars are so staggeringly vast compared to the physical size of the stars themselves. If you shrunk the sun down to the size of a ping pong ball, the nearest star would be another ping pong ball hundreds of miles away.
Hundreds of miles.
Yeah. Because of that immense emptiness, when these two huge galaxies collide, the statistical probability of any two stars actually hitting each other is practically zero.
So they don't crash into each other, they just slip past one another in the dark. It is less like a car crash and more like two massive swarms of bees flying directly through one another.
That's the perfect analogy. The swarms mingle. Over millions of years, the combined gravity of the two massive galaxies will violently scramble their structures.
So the pinwheel is gone.
Yes, those beautiful spiral arms will be pulled out into long, chaotic loops and tails of gas and stars. Eventually, the chaos will settle down, and the two galaxies will reshape into something entirely new, most likely a giant, featureless elliptical galaxy.
One of those retired communities.
Exactly. But our own sun and whatever is left of our solar system will survive the encounter unharmed. We will simply be flung into a brand new orbit within the newly combined supergalaxy.
That is just incredible. The next time you are outside on a dark night and you let your eyes adjust and you look up at that faint milky band of light, remember the sheer weight of what you were looking at.
It's not just a pretty view.
No, it's a structure that was meticulously assembled over more than 10 billion years. It started from primordial hydrogen pooling into invisible dark matter valleys. It grew into a behemoth by swallowing its smaller neighbors. It spins endlessly around a monstrous supermassive black hole, and it is currently falling towards a future collision that will erase its spiral shape forever.
The most profound realization from the essay, I think, is the perspective it gives us. We are experiencing this epic 10 billion year history from the inside out.
From our little chocolate chip.
Right. We are standing on one small planet, orbiting one perfectly average star among hundreds of billions of others. And we are looking out into the dark using eyes and scientific instruments that took the entire history of the cosmos to develop. We figured out how our galactic home was built while trapped inside the walls.
It is an absolute triumph of human curiosity.
Uh-huh.
But I want to leave you with a final thought to mull over. Something that stretches this timeline to its absolute limit.
Always expanding the horizon.
We know the universe is expanding, and that expansion is accelerating. While our local galaxies, like Andromeda and the Milky Way, have enough gravity to pull together and merge, the expansion of space is driving all the other distant galaxies away from us faster and faster.
Right, space itself is stretching.
Exactly. So, billions of years from now, after we have merged with Andromeda into one giant supergalaxy, that accelerating expansion will eventually push every other galaxy beyond our observable horizon.
The light will literally no longer be able to reach us.
Yes, whoever or whatever is living on a planet in our supergalaxy in the deep future will look up into the night sky and see their own stars. But beyond that, complete and utter blackness.
Wow.
They will have absolutely no evidence that the rest of the universe ever existed. They will think their isolated, merged galaxy is the only thing in the entire cosmos. Keep looking up while we still can.